Sorry. Uh, Sorry for that. I didn't start. That's why. Okay. So that's why you can see that the daily average load is the number of units generates in the day divided by 24 hours. And we also told that the average load is always against the per hour. Okay, the per hour. When you have the 24 hours in a daily basis, so you get the daily average load. For monthly average load, you represent 30 into 24 hours, and for the yearly average load, you just multiply with 12 months, then 30 days into 24 hours. You get the total hour of 8,760. This is the total hours in a year. Okay, in an annum or year, annual year. So this how we can get the daily average load, the monthly average load, or the yearly average load. So if you go, the next is load factor. Load factor is just the ratio of the average load by maximum demand, the average load of maximum demand. And we all already discussed that the maximum demand is the peak value of that load curve, and average load is the the summation of everything, and then divided by the number of hours. So from there on also we can say that the average load is always less than maximum demand, because maximum demand is only one value while calculating the average load. So the other values, or the other values, are always less than maximum demand. So when we sum that, the average always becomes less than maximum demand. So for that also the load factor is also less than 1. Okay, I think everyone knows that. Just I'm just going this for just the refreshment, so that when we start the mathematics, nobody just so where this comes from. Next, the diversity factor. We discussed so much about this diversity factor, that individual sum divided by the maximum demand of the power station. And we also told that that individually, when we calculate the maximum demand, definitely the summation will be much more higher. Okay, but the maximum demand of the power station will be not that value, because of we do not use our maximum demands at the same time. So when we calculate the maximum demand for the power station of an area, that becomes less when we get those individual maximum demand and make the summation. Definitely that value is higher. So that's why the upper value is higher and the lower value is in the lower. So the diversity factor is always greater than 1. So the diversity factor is always greater than 1. Okay, so load factor is less than 1, but the diversity factor is always greater than 1. So that was the diversity factor. Last, let's see anything else. Okay, the plant capacity factor. We discussed the plant capacity factor is the average demand by plant capacity. We finally conclude here. Okay, so how we get there? So basically the plant capacity factor is that actually energy produced, but the maximum energy that could have been produced. We give an example of a particular person who can pull off how much weight. He has the capacity of pulling 100 kg of weight, but he is pulling off 50 kg. So basically 50 divided by 100, that is the plant capacity factor, or his capacity factor. So average demand, basically that is the average amount of power that plant, or that power plant is producing, but he has the particular capacity. Suppose he is producing 12 and he has the capacity of 24. So he is using his 50%. So at that time the plant capacity factor will be 0.5. Okay, so that's how we conclude the plant capacity factor. And similarly the plant use factor, that how much hour you have used, that is station output in the kilowatt hour. If you sum the kilowatt hour, then divided by the capacity and the hour we've used, how much hour you have used, that is the plant use factor. Okay, so is there anything else? Let me check. Okay, last but not the least, the units generated per annum. Per annum means per year. Per year, how much energy we generate. That is the that how we represent it mathematically. We finally conclude here that the load factor is the average load by maximum demand, and average load, we can tell that average load equals to maximum demand into load factor. Okay, so unit generated per year, we can take that the average load in every hour and hours in a year. So that is already we discussed 8,760. And if we replace the average load using maximum demand into load factor, we get this equation that maximum demand into load factor into 8,760. That is annually how much energy or how much kilowatt hour we produce. Okay, so that was just the memory refreshment so that we can move forward for that. uh, Let me check. Please, everybody try to give your role. I think that students have already given, but still, if you're missing, try to give your role. So let me check this first example. That's what it's saying. Okay. So in the example, the first thing is let's read the example. That the power station has a daily load curve as under. The daily load curve is not given, but there are some values given here. That 260 megawatt for 6 hours. So that power station works or produce 260 megawatt per 6 hours. Okay. Then 200 megawatt for 8 hours. 8 hours 200 megawatt. 160 megawatt for 4 hours, and the 100 megawatt for 6 hours. So totally we can say that 24 hours. These are the amount the power station produce. So if you just clear everything. So the question is that if the power station is equipped with 4 set of 75 megawatt each. So basically there are 4 units on that power station, and calculate the daily load factor, the plant capacity factor, and the daily requirement if the calorific value of oil used is something like that, and the average, that is totally different concept, we'll discuss later. So let's find out the daily load factor and the capacity factor of this plant. So you can draw this information into diagram, or without drawing you can also there forward. So from this 4 value, we can definitely see that 260 megawatt is the highest value. 260 megawatt is the highest value, and from there we can say that this is the maximum demand of the power station, isn't it? The 260 megawatt is the maximum demand of that power station. So for load factor, we know that to find out the load factor, we need two value. One is average demand divided by maximum demand. So maximum demand, we already can say that this is 260 megawatt, and average demand, to make that we need to calculate. So you see that the maximum demand of the station is 260 megawatt. That is quite absolutely okay. Now calculate the whole energy produced throughout the whole day. Okay, that will give you that 260 for 6 hours, 200 for 8 hours, 160 for 4 hours, and finally 100 for 6 hours. So these are the 4 data. If we just sum everything, the amount of kilowatt hour that we get, that will be the amount of power they generated throughout the day. So in a day, we know that we have 24 hours. So if we divide this value by 24 hours, we will get the average demand. Okay, we will get the average demand or average load. So the daily load factor, if the what will be the daily load factor? The daily load factor will be the, sir, average demand by maximum demand. Okay. So average demand we can get from this value, this divided by 24. This is divided by 24, and maximum demand we already discussed 260. So you see that from the daily load factor, this is divided by 24 and divided by the maximum demand 260. So from there on, if we get the percentage, we get the multiply with the 100, and we get the 70.5%. That is the daily load factor. Okay. The next thing is that the plant capacity factor. We know that the plant capacity factor equation is average demand by plant capacity. Average demand by plant capacity. Average demand we can easily get from this divided by 24. We get this is the average demand. Okay. And station capacity, there is already told that, so we have 4 sets of 75 megawatt generator. So that means if we multiply 4 into 75, we get the total capacity. So 4 into 75, that is 300 megawatt is the capacity. 300. So the plant capacity factor will be the average demand divided by the average demand divided by the station or plant capacity. That is the dividation. We get the finally that 61.1% basically we are using for the plant capacity. Okay, very simple. So let's go to the last part, that how much oil, no, daily requirement of oil, how much oil that is required here. So it's very interesting information is given. See that, sir, if the calorific value of oil used here, that 10,000 kilocalorie per kg. What is calorific value? That is the important thing. What is calorific value? The calorific value is of a particular fuel. If you burn that fuel, for 1 kg of fuel, how much heat we produce, that is the calorific value. Okay. So the calorific value, if it is given, that means that if we burn 1 kg of that fuel, it can be oil, it can be coal, everything, it can be gas. The calorific value is the the actual value amount of heat produced when we burn that amount of fuel. So we have already given that for 1 kg of oil, we get 10,000 kilocalorie heat. 10,000 kilocalorie that is given us. The 10,000 kilocalorie heat that is given to us. Okay. And one more information is given, that the average heat rate of station is 2,860 kilowatt, sorry, not kilowatt, kilocalorie per kilowatt hour. That means it is telling that to generate 1 kilowatt hour energy, we require 2,860 kilocalorie to generate only 1 kilowatt hour. So we have already the daily requirement. They are asking for the daily requirement. We have already find out the value of the daily power generation in the kilowatt hour, and they are giving us for 1 kilowatt hour. So we just multiply those value this. So the heat required per day, this is the for 1 kilowatt hour, this is the total kilowatt hour generated for particular day. If we just multiply that, we will get the total heat. Okay. So we need the fuel, how much fuel we require for that particular day. So this is the total amount of heat, and there the first information is given that 10,000 kilocalorie for 1 kg. So if we just divide this 10,000 kilocalorie by total amount of heat, we'll get the exact amount of kg or exact amount of fuel that is required for particular that day. So we just divide that 1,000, we get that is this amount of huge amount of oil. So basically 1,256.4 tons of fuel required for that particular power station in a daily basis. I think we understand. Just is the normal calculations, just for the understanding purpose I discussed. So let's move the next. It will be probably very easy. That a power station has a daily load curve given from 6 to 6, total 24 hours load distribution is given. So plot the load curve and also load duration curve, and also calculate the. It's a very easy problems, I think, that from 6 to 8, so you just divide from everything from 6 to 8, 8 to 12, 12 to 16, 16 to 20, 20 to 25, 24, and 24 to 6. So basically we started from 0, that is at midnight 12, and 24 also represents the midnight 12, so total 24 hours. So from 12 at midnight, from 12, okay, what will be the, from 12 is 24, because 24 is, at night 12, 24 to 6, that is, the morning 6, so the load is 20 megawatt. So you just see that from 24, from midnight to 6 it is 20, and even from 6 to 8 it is also 20. So we just extend that line to 8. Okay, so till 8 the capacity is, or the load demand is 20. So from 8 to 12 it is 40, so we just increase that. 8 to 12 is 40. Finally 12 to 16, that means the afternoon 4, that is 60. So 12 to 16, that is 60, we just draw. And then finally from 16 to 20, that means from afternoon 4 to 8, night 8, so that will be 20. And after that, from from 8 to at midnight 12, that is 50. So this is the load curve. Okay, this is the load curve of that particular information that is given. So for the load duration curve, we don't need to count the clock anymore. We need to count the number of hours, and also the ascending manner. Okay, the highest value will be the first one, then the lowest value, then the lowest value, then the lowest value. So here, for drawing the load curve, sorry, load duration curve, at first we need to find out what is the highest value. We see the highest value is 60, then is the 50, then 40, and finally 20. Okay, so for 60, how many hours it has? 12 to 16, that means 4 hours. So 0 to 4 hours, that is 60. You can see 0 to 4 hours, that is 60. Then 50, how many hours? 20 to 24, that is 4 hours. So 4 to 8, next 4 hours, that is 50. Then the 40, how many hours? So it is also 4 hours. So 4 hours, that is 40. And the rest of the 12 hours will be, the capacity will be 12 20 megawatt. The capacity will be 20 megawatt. So you see that the rest of the 12 hours, it is 20. Okay, so that's how the transformation of load curve to load duration curve. So what is the advantage? The advantage is that you can, from this load duration curve, you can easily call that what is the how many hours are of a particular load amount is going on. Okay, so you can, these information are very much available in your eyes, that we can easily say that the 20 megawatt hours are 12 hours, 20 megawatt load are 12 hours throughout the day. So you can easily tell those information. Let's calculate the energy generated per day. You can calculate from any graph, from this graph also and this graph also. Those two graphs looks like different, but the area is same because those are rectangles. The area is same. So we just need to find out the area of every rectangle. This one, first of all, this one, then the next one, then the next one, then finally the next one. We just have the value of 60 into 4, then 50 into 4, then 40 into 4, the two, the two sides, 40 into the rectangle. 40 into 4, and finally the 20 into 12. So if we just sum all those, we'll get the total amount of energy generated of that particular day. So you can see by your you know eyes that the same thing has done. The 20 into 8, 40 into 4, 60 into 4, finally 20 into 4, and 50 into 5, 4. So basically they have done from these graph also. But same thing, if you find the area from this graph or this graph, both will be same, because there is nothing change in the area from these two graphs, though it looks like different in structure, but the area will be the same. Okay, so that's how very it was very easy one. But we showed that how the load curve and the load duration curve is not transferred. We have to convert from load curve to load duration curve. So finally, one more. This is the last example we will discuss before we finish our class. Uh, Interestingly, let's see what it is told. It is told that the annual load curve of a certain power station can be considered as a straight line. Okay, a straight line from 20 megawatt to 4 megawatt. Okay, so the load duration curve, basically the load duration curve is given from 20 megawatt to 4 megawatt. To meet this load, 3 turbine generator units, 2 rated at 10 megawatt, and 1 is 5 megawatt. So basically 10 plus 10 plus 5, 25 megawatt, that is total capacity. So determine the installed capacity. We already told 25 megawatt it will be. The plant factor, the units generated per annum, the load factor, and finally the utilization factor. So this is the load duration curve. The starting point is 20, the end point is 4. Okay, so there is nothing, lack of information is given here. And this is the total year, throughout the year, annual total year it is given. And the highest, definitely from this load duration curve, we can definitely say the maximum demand is 20. Okay, the maximum demand is 20 megawatt. That is the maximum demand. So what will be the average demand? The average demand is very interesting, as there is no information is given, so we can take the middle one. We can take the highest value of 20, we can take the lowest value 4. So 20 plus 4 divided by 2, take the average. So basically 12 megawatt will be the high average. 12 megawatt will be the average. Okay, so maximum is 20, average is 12. Maximum is 20 and average is 12, and the installed capacity is 10 plus 10 plus 5, because 2 rated at 10 megawatt and 1 rated at 5 megawatt. So basically 10 plus 10 plus 5, 25 megawatt, that is the installed capacity. So we already discussed the installed capacity, that is finished. Plant factor. Okay, so let's go to the next slide, that what they discussed. Okay, so plant factor means the plant capacity factor. Okay, the plant capacity factor, we all know that the average demand by the plant capacity, I already find out what is the average demand, taking just the two value, because there is nothing given here any. Just taking the average of these two value, we get the 12 megawatt. So we calculated the plant capacity already, 10 plus 10 plus 5, that is 25 megawatt, and the average demand is 12 megawatt. So if we divide those two value, we get the 0.48, that is 48% plant capacity factor. Okay, we are using, or they are using 48% of its total capacity. So the that is done. So that what will be the next? Let's check. The next is the units generated per annum, and the load factor and the utilization factor. Okay, so units total generated power throughout the year. So basically this is the area. Okay, the area under this load duration curve, this total area is the total units generated per annum. So how to find out this area? We can find out so many ways. Either we can find out the area of this triangle, and find out the area of this rectangle and sum. This is one process. And the other process will be, if we consider this as a trapezium, this is a trapezium because it has two parallel lines. You see that this is the two parallel lines, and so this is a trapezium. So we know that the area of the trapezium is summation of these two sides, summation of these two sides divided by 2 plus the distance between the vertical distance between the two lines. So that's why here the trapezium area has been calculated. So the two side is, one is, this is 4,000, you know, this is 4,000, this is 20,000. So they've taken 4,000 and 20,000 divided by 2, that means half, and the distance between these two sides. So the distance is basically, 0 to 8,760. So that is the distance they put, and finally they got the total area. You can use this formula, or you can use the, the triangle and the rectangle area. Both the value will be the same because the area are always same. This is geometry, so there will be no change. So that is the unit generates per area, per year, sorry, not area, per year. So finally the load factor, we know that load factor is the average demand by maximum demand. Average demand by maximum demand. Average demand we already discussed 12. The maximum demand we can say that this is 20. So 12 by 20, that is load factor is 60%. Okay, 60%. And finally the utilization factor, that how much maximum you have utilized the total capacity. The utilization factor, the maximum demand was 20 but your capacity was 25. So basically you are maximum at a time using 80% of your capacity. Okay, maximum you are using 80% of your, or utilizing your 80% of your capacity. Okay, so that was the easiest way possible how to solve those. And I hope that looks like a very easy for you. Total 21 students have joined. Please give your role in the chat box if you didn't give here. So that's it for today. Okay, so I think I believe that there shouldn't be any question because we have discussed this type of mathematics so many times, and today whatever we discussed was not a tough one. So still I'm stopping this share and going back to my students, and and unmuting all. If you have any questions or and discussions you want to share with me, you can ask me. My students, everyone is unmuted. I unmuted from my side. Is there any question, my students?
Sir.
Yes, sir. Who?
Engineer Bahsad.
Acha. Okay, okay. Yeah, tell.
Sir, and from where did you get 1/2? And as you know that previous two mathematics, we get 1/2. 1/2 as I can see 2 times. From where did you get that number 1/2?
From, okay, let me share screen one more time. I'm not getting which part you are telling about. 1/2 means this 1 by
Like
2.
that.
This 1 by 2.
Yeah.
This 1 by 2.
Yes, sir.
Okay, this is the law of trapezium. Okay, if you just go through the what is the trapezium area. The trapezium area is something like that. Let me draw the trapezium. Okay, this is your home task. You have to submit what is the area equation of trapezium next class. Okay, still I'm telling you. In the trapezium, if there are two parallel lines, and suppose this is the perpendicular distance from these two lines, the area of this trapezium will be, suppose this is AB and this is CD. You will give me the assignment. What is the area of the trapezium? At that time, the area will be AB plus CD. AB plus CD. Okay, divided by 2. divided by 2 and the distance. Suppose this distance is h into h. So whatever the 1 by 2 you're talking about, this is these two. Okay, am I clear?
Yes, sir.
You will submit the trapezium area equation in the next class. You forgot. Okay. Anything else, my student? Anything else? My students? Everybody is unmuted. Yeah, I have unmuted everyone. But any more question?
No, sir.
Okay. Okay. Have you given your everyone role? I
Yes, sir.
think so. I think so. So let's see you in the Tuesday with a new topic. And till then, you stay home, stay safe. And I'm giving you this class lecture as soon as finish this class, and also the video lecture as soon as I finish this class. So take care yourself, and also be safe.